Alright, so back for some more. Let's go ahead and solve. Basically, again, we're solving trig equations where the period is changing, right? And even in some cases where the period hasn't changed, when we use some identities, we know that it will have changed. So we'll take a look at all that. So here we got the sine squared of 2x minus 3. So I'm definitely seeing a quadratic where we can essentially use the square root property at some point. So if I add 3 and divide by 4, we end up with sine squared of 2x is equal to, that's going to be 3/4. So if I invoke a square root, we have sine of 2x is plus or minus the square root of 3 over 2. So we basically have solutions in every quadrant, right? So the square root of 3 over 2 tells us that we're dealing with a 60-degree reference, all right, or what we know to be pi over 3 in radian mode. And then since we're plus or minus, that means we have solutions in every single quadrant with that pi over 3 reference. So what are our solutions, right? So I'm going to go ahead and just say, so our 2x at the moment equals, it could equal pi over 3. It could equal 2 pi over 3. It could equal 4 pi over 3 or 5 pi over 3. So all those are in the first rev. Since we are multiplying the x by 2, this means that the new period, right, is 2 pi over 2 is pi. So what's happening from 0 to pi, right, there's 2 cycles we go through in a normal period. So that means I've got to go a second revolution out to make sure I get everything when I divide out the 2. So again, we're going to be adding 2 pi to everything, and 2 pi is 6 pi over 3. So when I do it to this guy, we get 7 pi over 3, we get 8 pi over 3, we get 10 pi over 3, and we get 11 pi over 3. So there's basically all the solutions in the first rev and all their coterminal angles in the second rev. So to solve for x, I'm going to multiply everything by a half, right? That'll get x by itself, and I essentially have to multiply everything over here by a half. So that gives us pi over 6. The 2's cancel out here, leaving us with pi over 3. A 2 will cancel out, leaving us with 2 pi over 3. And then we end up with 5 pi over 6. So there's our 3 angles in the first rev, or at least converting the first rev ones. Here, 7 pi over 6. 2 will divide out with the 8, giving us 4 pi over 3. The 2 will divide out with the 10, giving us 5 pi over 3. And then it looks like we end up with 11 pi over 6. So there would be our 8 angles within the first revolution that solve that inequality, solve that equality by using the fact that our angle, right, our period has changed. So what happened from 0 to 2 pi is actually happening from 0 to pi. So we have 2 cycles. So to get all the solutions, I'll go out 2 revolutions to handle the division by 2, which condenses everything down to what we need. All right, so the next one, again, there's actually a lot of ways to solve it, but the way that I'm going to see this is I see, right, this is one of our double angle formulas for cosine. So this is cosine of 2x equals to 0. And so, again, we're talking about our new period is pi. So just like this one, we're going to have to go out 2 revolutions to get them all. So our 2x, well, in the first revolution, cosine is equal to 0 at pi over 2 and 3 pi over 2. If we go to the next revolution, again, we're adding 2 pi, which means we're adding 4 pi over 2. So that gives us 5 pi over 2 and 7 pi over 2. So there's basically all our solutions, right, in the first rev and their coterminal angles in the second rev. Now to condense everything, I'm going to multiply everything by a half. That puts x by itself, and we end up with here, it looks like pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So basically all those angles do in fact fall within the first 0 to 2 pi rotation. So we got them all. Those are all the guys that solve that particular equation at the moment. All right, so the next one, I have cosine of 2x plus cosine of 2x, and I'm squaring it. So again, a lot of stuff going on there. Lots of ways to approach this. I'm going to approach it by expanding everything out. So let's see where that takes us. So we're going to have cosine 2x plus cosine 2x times sine 2x plus cosine 2x. So let's see if my idea takes us somewhere. If it doesn't, we'll just start over. All right, and so in this case, we end up, if we FOIL everything out, we end up with sine squared 2x, right, plus a sine 2x cosine 2x. We have another, it's in different order, but it's the same thing, sine 2x cosine 2x, and then we have plus a cosine squared 2x. So sine squared and cosine squared, that's 1. Putting those together, we have plus 2 sine 2x cosine 2x. And of course, 2 sine x cosine x, that's 1 plus sine of 4x, because that's our double angle for sine. And since I'm doubling the angle, it becomes 4x. So what that tells us then is that this is 1 plus the sine of 4x equals to 0. So moving some things around, we have sine of 4x equals -1. And so basically, our period is being, our new period, right, is going from 2 pi over 4 to pi over 2. So this tells us, since we're condensing, right, what happens from 0 to 2 pi to 0 to pi over 2, this tells us that we're going through four cycles. So we basically have to carry this through. Oh my goodness, I think I was off the page there. I apologize. All right, so we have to go through 4 periods with this guy. So 4x, right? When is sine equal to -1? Well, that happens in the first revolution at 3 pi over 2. So in the second revolution, if I add 2 pi to that, right, that gives us, that's 4, that's 7 pi over 2. If I add to that, that gives us 11 pi over 2. And if I add to that, that's 15 pi over 2. So first rev, second rev, third rev, fourth rev. I just keep adding 2 pi, which is 4 pi over 2 in those cases. So now if I multiply everybody by 1/4, that'll get the x by itself, and it'll condense all these into the first rev. So this is 3 pi over 8, looks good. This is 7 pi over 8, that also looks good. That's 11 pi over 8, which looks good, and 15 pi over 8, because 16 over 8 is 2. So all of those fall within the first revolution, so we're safe and sound. So there you go. So we used some algebra. We used a couple of identities, right? The Pythagorean identity giving us 1, and then the double angle for sine giving us another. That condensed it to basically a quadruple angle, and then I was able to use my little trick going out some angles there and getting my value. So for the next one, again, this looks a little tough. At the beginning, I don't see any double angles, any triple angles, or anything crazy like that. So let's go ahead. How about we rewrite this? Secant is 1 over cosine, right? And tangent is sine x over cosine, right? And this is all over 1. So let's see what happens here. So if I clear out the radical, or if I clear out the denominator, right, I'm going to multiply everything by cosine. And so what we end up with is, over here we end up with 1 minus the sine of x equals the cosine of x. So that's not, I don't know if that's really getting us anywhere. Let's just keep trying. So, this one is pretty tough. So let's move this over. We got 1 equals the cosine of x plus the sine of x. I'm wondering if I miswrote this somehow, because I'm not getting any double angles or anything nice to use here. I might have miswrote this, you guys. So let me go ahead and try another one. Let's try it. So we tried that. Let's 1 over cosine. Here we go, right? So what we know, right, is that tangent squared x plus 1 is secant squared x. So let's try that route. So if I replace, but I don't have tangent squared. Yeah, you know what, you guys? I think I miswrote this. I think I probably would need a secant squared or cosine squared, tangent squared. So I think I miswrote that. I can't even use that trick. So I was thinking maybe I can turn it into, we have secant. If I can get secant squared, we got it. But we only have a tangent, not a tangent squared. So I actually think I miswrote this. I apologize. I'm going to go back. Maybe I'll recut a video, or I think I did, you know, with those three, we got a lot of our action, and I've got more coming on the way. So maybe I just table that. I apologize for a bad example there at the end. I'm missing something, so we'll figure that out as we go. Alrighty, but hopefully you saw that trick. We used our trig identities in combination with our trick to get the job done. Keep on learning, keep on growing, and I'll see you guys in the next video.